In the last video, we discussed why it is so difficult to shift travel from the most commonly used mode of transportation, which is a personal vehicle. The success of energy transition will ultimately depend on long-term behavior changes. In this video, you will learn how to analyze and quantify the benefits from mode shift and infrastructure changes. To calculate and perform emissions inventory, we will be using emission factors. Each pollutant will have a different emission factor. Each pollutant will also be defined per time of operation, unit of fuel consumed, and/or distance traveled. Very commonly, we use grams per kilometer. Common air pollutants include carbon dioxide, non-methane hydrocarbons, particulate matter, that is a term used for a mixture of solid particles and liquid droplets found in the air. Then we also have nitrogen oxides, carbon monoxide, sulfur dioxide. To perform emission inventory, we will use the general equation that looks like here on the slide, where EI is emission of pollutant I in grams, FCJM means fuel consumption of vehicle category J using fuel M, that's usually defined in kilograms, and EFIJM is fuel consumption specific emission factor of pollutant I for vehicle category J and fuel M in grams per kilogram. In essence, you multiply fuel specific emission factor of pollutant by the amount of fuel used by a vehicle of a certain category to arrive at the amount of pollutant emitted in a particular process. We will next simplify this equation to focus on a specific case and the number of kilometers driven instead of the number of kilograms of fuel used, and we will then multiply the emission factor per vehicle type and fuel type, grams per kilometer, by the number of cars per hour and the number of kilometers in the segment of interest. In our example today, we will evaluate a segment of a highway with a particular hourly traffic. Now, consider a highway of 10 kilometers in length that has 3 lanes in a single direction. A total of 300 cars travel along each lane per hour. Each car carries on average 1.5 persons. The traffic of cars that consume gasoline causes air pollutant emission, as shown in this table. And for that reason, we aim to minimize air pollutant emissions. The local authorities decided to use one of the highway lanes to implement an exclusive bus lane system. We will assume that the expected car traffic will be reduced proportionally to the reduction in the number of lanes available for its traffic. However, please note that in reality, it may not often be the case. Consider that all the people who used cars and stopped using the express lane started to use buses, which again is a very general assumption, but let's say the bus lane is very attractive. It is expected that one bus, which uses diesel oil, transports 60 passengers. The question is to estimate the expected variation in air pollutant emissions per type of pollutant after the implementation of the exclusive bus lane. We start from producing the baseline emissions inventory, considering the situation when only cars travel along the way, and compare the results with the alternative situation in which there are 2 car lanes and 1 bus lane. The emission factors are shown in grams per kilometer for both cars and buses. Step 1. The study area is a road segment used for the traffic of cars and buses with 3 lanes. For the baseline, the 3 lanes are used for cars only, and in the alternative scenario, 2 lanes are used for cars and 1 for buses. Step 2. For the baseline, the volume noted as V of 300 cars per lane will be considered, and we will arrive to 300 times 3 equals 900 cars per hour in the segment. The alternative situation considers a volume of 300 cars per hour along 2 lanes only, so that will be 600 cars per hour, and an equivalent bus flow that carry the passengers who stopped using one of the lanes in this segment, and that will be about 7.5 buses per hour in one lane. And then 1.5 was the occupancy per car, and 60 was the assumed number of passengers in each bus. Step 3. The sources of air pollutant emissions will be based on time of 1 hour. However, in reality, it could be often 1 year or any other time period. The study area of 10 kilometers will only be considered. Step 4. Let's go to the calculation part. We have already calculated that 900 cars will be traveling in 1 hour on the highway. So V1 is equal 900. And this will be our baseline. Calculation of the car traffic volume in the alternative situation after the bus lane implementation will be V2 and equal to 600 cars per hour. Because we expect mode shift due to the bus lane, we have to see how many people will switch. As we recall the assumption stating that all passengers in that lane will switch to the bus, we calculate the number of passengers per lane by multiplying 300 by an average of 1.5 passenger per vehicle and arrive at 450 passengers per lane per hour. As per the table provided to us, we will focus now on 5 pollutants. Let's get to it. Knowing we have 450 passengers traveling in the future bus lane, we can now determine how many buses they'll need. We divide 450 by 60 and again arrive at 8 buses. Now let's calculate the baseline emissions. Considering 10 kilometers of highway and 3 car lanes, using the equation emission factors, that is given to us in grams per kilometer times number of cars per hour times number of kilometers in that segment. And we arrive for CO2 at 2.25 kilograms per hour. We repeat it for the other pollutants and we calculate the total emissions for NOx and MHC, particulate matter, and lastly for CO2. And that will be our largest one because it's 855 tons per hour. Now we will calculate emissions in the alternative situation so that we will consider 10 kilometers of highway, 2 car lanes, and 1 bus lane. First, calculation of the emissions for 2 car lanes. We again use the same technique and multiply emission factor from the table by the number of cars and the length of the segment. And for CO2, we have 1.5 kilograms per hour. We do the same for other pollutants. And again, CO2 will be the largest value. Now, calculation of emissions. 1 bus lane. Same method for CO2, for NOx, and all the other pollutants. And again, CO2, no surprises, has the higher number of 68 kilograms. Now that we have the emission inventory for the base case and the emission inventory for the case after the bus lane implementation, we can compare them. And that's step 5. Step 5 aims to evaluate the variation in emissions between the baseline and the alternative scenario after the intervention. So we simply subtract these numbers and we see that most of them but one decreased. It can be seen that there was an increase in the emissions of NOx in mass per time unit and a decrease in the emissions of all the other air pollutants with the introduction of the bus lane. We have observed total reduction in air pollutant emissions even though the emission factor for diesel buses is higher than those for gasoline cars. As you expect, the results would be much more different if the bus was electric. Next, you'll have an opportunity to practice this method. In the next video, we will discuss more of a qualitative ways to approximate impact of transport-related interventions on environment, as well as we will define average marginal abatement curves and mitigation potential.